For over 500 days, Earth has been receiving a repeating radio signal from deep space that follows a strict 16-day schedule. Fast radio bursts, or FRBs, are flashes of energy lasting only milliseconds. Because they are so intense, they were historically viewed as one-off cataclysmic events, the final signatures of a star being destroyed. But data from the Chime Telescope Observatory in British Columbia revealed a source that didn't fit the pattern of a terminal explosion. This newly discovered repeating source is called FRB 180916. The signal operates on a 16.35-day period. It features a 5-day active phase of frequent bursts, followed by 11 days of silence. Within that window, individual bursts arrive erratically, but the 16-day cycle returns with statistical certainty, ruling out random chance. This repetition shifts the requirements for the source. It proves the object isn't being destroyed by its own energy, but is a stable astrophysical system capable of resetting and firing again. Using high-resolution interferometry, astronomers localize the source to a star-forming region in the outskirts of a massive spiral galaxy. That galaxy is roughly 500 million light-years away from Earth. Traversing 500 million light-years requires a pulse energy of approximately 10 to the 38 ergs. That is millions of times more powerful than the brightest giant pulses recorded from the Crab pulsar in our own galaxy. Understanding how a single object can generate that much power while maintaining a 16-day cycle is the central challenge of the investigation. One leading explanation is called orbital modulation. This model suggests the source is a neutron star locked in a tight binary orbit with a massive, super-hot companion star. These massive stars eject dense stellar winds into the space around them, creating a cloud of plasma that can scatter or absorb radio waves. In this scenario, the 16.35-day cycle is the time it takes the neutron star to complete one full 16-day orbit around its companion. The 5-day active window corresponds to the specific phase of the orbit where the neutron star clears the densest part of the wind, allowing its signal to reach Earth. This model relies on standard orbital geometry rather than internal stellar physics to explain why the signal disappears for 11 days at a time. An alternative hypothesis focuses on the internal state of a single, isolated magnetar, a neutron star with a magnetic field 1,000 times stronger than a typical pulsar. Magnetic fields of this magnitude are strong enough to physically deform the star's crust, pulling it into a slightly asymmetrical shape. This asymmetry causes the star to undergo free precession. While it spins rapidly on its axis, the star also slowly wobbles along a secondary path, wobbling much like a destabilized spinning top. If the magnetar is emitting a beam of radio waves, that beam will sweep across the sky as the star wobbles. The 16-day cycle is the time it takes for that wobbling beam to point directly at Earth. By utilizing the known physics of magnetic deformation, this model explains the periodicity without the need for a companion star. A third possibility is that we are seeing an ultra-long period magnetar, a star that takes 16 days to complete a single rotation. Most magnetars spin multiple times per second. To slow a star down to one rotation every 16 days requires an aggressive braking mechanism. As this chart indicates, episodic events like giant flares or particle winds can drain the star's angular momentum. To reach a 16-day rotation, a star needs an internal magnetic field exceeding 10 to the 16th Gauss, a rare condition even among magnetars. However, high-energy observatories like SWIFT and AGILE have monitored the source during its active phases and detected no X-ray or gamma-ray counterparts. This absence of high-energy emission creates a strict limit. Any proposed model must explain how the star can generate intense radio bursts without bleeding off detectable energy at other wavelengths. While the slow spinner fits the radio timing, the lack of high-energy radiation makes it difficult to reconcile with our current understanding of how magnetars dissipate their magnetic energy. The data presents 3 specific constraints: a pinpoint location in a distant galaxy, an output of 10 to the 38 ergs, and a repeating 16.35-day cycle. This diagram maps the limits of theoretical physics. While we have models for orbital winds and precessing stars, each one struggles to account for the total absence of high-energy data. Despite monitoring every active cycle since its discovery, the mechanism driving FRB 180916 remains a subject of intense debate among astrophysicists. The existence of this signal 500 million light-years away suggests our most advanced models are just beginning to capture the physics of the extreme universe.